Dear students, in this lecture, we will discuss about Kirchhoff's voltage law and mesh analysis. So Kirchhoff's voltage law is basically the law which states that in any electrical network, in a mesh of that electrical network, the net voltage is zero. The total voltage or the net voltage in any loop of the electrical network is zero. So here summation of all the voltages is equal to zero, right? So when we say all the voltages, we actually mean to say that there are the voltages present in the network which are from the sources and which are due to the voltage drops across the resistive elements that are present in the network, right? Now, this Kirchhoff's voltage law basically is used to simplify the complex electrical networks, and it signifies the law of conservation of energy. When we say that in a loop, let us consider a circuit, a small circuit with one mesh. Let us say E1 is the voltage here or EMF here, and this is, let us say, one resistance, this is one more resistance, and this is one more resistance. So this is, for example, R1, this is, for example, R2, this is, for example, R3. So as per the definition of KVL, the net voltage in this particular loop is zero, right? So when we say the net voltage in this loop is zero, so that means the total energy is conserved in this network. Now that means whatever energy is being delivered by this particular source, so it is, it is delivering the energy, and these three elements are dissipating that energy, right? So that energy is basically conserved. Okay, so whatever energy is delivered is being dissipated or utilized by the electrical network, right? The circuit elements basically. So now there are two things basically in this particular network, if you have noticed or observed. The one thing is that there is a source basically which is connected and which is used to deliver the electrical energy to the network, and there are three resistances. So this has an EMF, this is an EMF, and this is your resistance, which will have certain voltage drop. It will have certain voltage drop across it. This will also have the voltage drop, this will also have the voltage drop. So that means when we say that energy delivered means the source EMF and is being utilized by the electrical network circuit elements, so we actually are saying that the total EMF in the loop is equal to total voltage drop, and this is what is being represented by this particular equation. Summation of all IR, what is I into R? It is generally assumed or taken as the voltage drop, and this is the EMF, this is from source, right? So that means the sum of all these, the algebraic sum of all these voltages, algebraic sum. Now when we say the algebraic sum, we actually intend to take the direction of the voltages or polarity of the voltages, right? So in sign convention also we discuss the same thing. So let us cover that thing here also. Okay, now how to take the sign convention. uh, for example, you have a resistance. Okay, this is the value R and some current I is flowing here, right? Now if you have two terminals of this particular resistance, so if your movement of the current in the mesh, movement of the current in the mesh is with the current in the branch. So this would become minus IR. So it is actually the voltage drop. It is actually the voltage drop. Now, if the second case is that there is a resistance, the same resistance, and if the branch current is this is your branch current, and in the movement of the current in the mesh, if the direction of the current in the mesh is opposite, unparalleled, so this would be plus IR. So this we call as rise in the voltage or voltage rise. Okay, now um, let us understand this concept here. Okay, now what is KVL? Now let us again take one voltage source or EMF source here. This is, let us say, E1, and then we take one more one resistance here, R1, then we take one more resistance here, which is R2, and then we take one more resistance here, let us say this is R3. Okay, so if the current in the branch is flowing like this, and there are four nodes A, B, C, and D. So let us assume that the current in mesh is anti-clockwise. It is anti, this is totally an assumption. It has nothing to do with the direction of current. We have assumed. Okay, we have discussed it many times that we can assume the direction of current. Arbitrary assumption can be taken. Okay, and because these are the bilateral circuits, bilateral electrical networks. So now that means the current is flowing like this. So that means the current in mesh is moving or circulating from A to D to C to B and B to back to A. So let VA is the voltage, because this is what we have studied in nodal analysis, that every node has a voltage. Okay, if two nodes are connected with a short path, those two nodes will have same voltage, right? Voltage at node A. Then now let us write it here, VA. Now we are moving from A to D, but the direction of voltage source is always from minus to plus. So these two are opposing. So I will write it minus E1. Then now we are moving in this direction. These two are opposing each other. They are not matching. So I'll take it as plus I R3, where I is the current. Okay, let us say I is the current flowing in this mesh. Now, the same current, this one is moving like this. So these two currents, branch current and mesh current, are not matching. So I'll take it as plus IR2. And then similarly, we'll take IR1. And we are coming back to the node A. We left out from the node A and we are entering the node A. So it can be taken as minus VA is equal to 0, or we can also take it as equal to VA, right? Now these 2 points, these two factors will be cancelled out here. Now what do we have? We have the rest of the equation which we can write, and that equation is, let us write that equation. It is minus E1 plus I R3 plus I R2 plus I R1 is equal to 0. So let us simplify this one. So we get E1 is equal to I R1 plus R2 plus R3. Okay, so what is this? This is the EMF connected to the electrical circuit or source basically. So this is EMF, and these all are voltage drops. So now this is what this equation represents. So that means in any given network, the net voltage effect is zero, or we can also say that the sum of all the EMFs, sum of all the voltage sources is equal to sum of all the voltage drops, right? So now let us go further. Now let us come to mesh analysis. So mesh analysis is basically a method or a technique which is used to solve the complex electrical networks using KVL. Okay, so KVL is used here to solve any electrical network using mesh analysis. What is mesh? Mesh is the elementary loop of the electrical network. What is elementary loop? A loop that cannot be subdivided into further loops, which does not have any other inner loop. All right. So the mesh analysis is basically used to determine the unknown quantities, which are mesh currents. Okay, KVL is used, mesh currents are determined, mesh currents are unknown quantities. Like in nodal analysis, the unknown quantities are node voltages. Similarly, here the unknown quantities are mesh currents. Now, how to solve an electrical network using mesh analysis? So these steps are summarized here. So let's read these steps one by one. The first thing that we do to solve any electrical network using mesh analysis is we identify. This is the first thing you have to do. We have to identify the number of meshes in the given electrical network. We can also take the loops, also outer loops and all that, that can also be considered, because ultimately mesh analysis utilizes KVL, and KVL, that means the Kirchhoff's voltage law, is used in a loop, and mesh is also a loop, right? Now, then the second thing that we do is we assign the circulating current to each mesh. That is, let us say I1, I2, this and that, blah, blah. So let us draw one network here side by side, so that it becomes easy for us to understand. So this is E1, this is, let us say, resistance connected here, resistance connected here, and then we have one more resistance connected here. We have one source again, which is EMF source, which is E2, and this is R1, this is R2. I'll take a different ink. This is R2, and this is, for example, no, this is, let us say, R3, and this is, let us say, R2. And the first thing is I will identify the number of meshes. How many number of meshes are there? Two. Okay, this one and this one, these two are the meshes basically, because these two do not have any other elementary or any other loop, inner loop basically. Okay, so the second thing is, what I will do is I will after identifying the number of meshes, I will assign some circulating current in these meshes. Okay, so you can take any direction, that is totally up to you. You can take either clockwise direction or anti-clockwise direction, but for simplicity, what we will do, we will take the same direction in each mesh. If we have taken the clockwise direction of the circulating current, we will take the same direction in mesh 2 also. That is totally for the convenience. Mesh currents are not the real currents, they are fictitious currents which are assumed just to solve a network, right? So I'll give them marking. Let us say I1 and I2 are the currents, right? Now, this source, let us say, delivers some current which flows in this direction, and this also delivers some current which flows in some direction. So I will take this direction here, right? This is how the currents are flowing in the branches. Currents are flowing in the branches, right? Now, okay. So As each mesh current enters as well as leaves the mesh elements, the mesh currents implicitly satisfy KCL. Now, what does it mean? It means that whatever current is entering at this particular junction, it is either is divided into two parts, or there may be a possibility that some currents are coming at this junction, and maybe some currents are leaving at this particular junction. So that means while solving a network using mesh analysis or KVL, KCL is also satisfied. It is not that when we are solving a network using KVL, we do not obey or follow KCL. It is by default followed, basically. It is by default obey it, right? It is preferable to assign the same direction of mesh current in each mesh. This is what I just discussed. This is just for simplicity. Otherwise, you can take any direction that you want, right? Then we will write the KVL equation of each mesh. Now let us write the KVL equation of mesh 1. So what will be the equation? It is E1 like this, and some drop is there, then some drop is there. So we'll see how it is written by in next slide, right? Now then after writing the KVL equation, now how many KVL equation we get? The KVL equations is equal to number of meshes. Okay, if the number of meshes are 2, then KVL equations are also 2. If they are n, then KVL equations are also equal to n. Now we'll solve these mesh equations. KVL equations are also known as mesh equations, so that we can determine the unknown quantities, which are mesh currents. Now, this is what I have written here. The number of KVL equations are equal to number of meshes in the network, and this is the example, right? So, while solving a network using mesh analysis, we will also observe, we will also see that no branch of the network shall have more than two currents. Like in this particular branch, this is the common branch here. This will have some net current basically. Okay, this will have some net current. Like this particular branch, this one external branch is nothing but it is having I1 current flowing in it, and this branch, this external, this is the independent mesh here. These two are independent meshes, but this is the common branch, and because this is the common branch, so it will have some net effect of the current, net effect of the current in it, right? Now let us solve this network, the same network which we were discussing here. Okay, so let us identify, let us find out the KVL equation of this network. The first thing while solving network is to identify the number of meshes. So how many meshes are there? One mesh and two mesh. So the meshes are A, B, D, A, and then we have B, C, D, B. So A, B, D, and then back to A. You can also give some marking here if you want, otherwise it is okay. A, B, D, A, and then B to C, and then D, and then back to A. So this is how these meshes will be analyzed or studied. Okay, you can also take the otherwise direction. Otherwise direction means you can also assume, I'll write it here, or you can also say that it is from A to D to B to A, or this is for mesh 1 and this is for mesh 2. Similarly, the other direction that can be assumed for mesh 1 is this one, and now that we can take the similar direction, because if I am taking it as clockwise in the second mesh, also I will take it as clockwise. If I am taking it as anti-clockwise in the second mesh, also I'll take it as anti-clockwise. And as I mentioned earlier, also it is totally for the sake of simplicity, nothing else. It has nothing to do with the standard direction of the current. So we'll take it as B, D, C, B. So this is, let us say, for mesh 2. You can follow any of these two directions, right? This is totally up to you. Now the first thing is identify the number of meshes, then assign some current to each mesh. So I have assigned here I1 and I2 are the currents, let us say. So now as you can see in this particular circuit, there are two independent branches and one common branch. So this is the common branch, basically this one is the common branch, and this one and this one means what you say, DAB and BCD are the independent branches. Now, why they are independent branches? Because they have a single current in them. They do not have a net effect of the current basically. So this will have a net effect of the current. So we can say that some current is flowing here like this, and some current is flowing here like this. So direction could be taken, in any uh, way. That is totally up to you. So this current is nothing but I1 basically. So, and this current is I2. Okay, and but this current will not have I1. This will have either I1 minus I2 or something I2 minus I1. Means some net current will be there, right? So the first thing is identify the number of meshes, assign some current, assume some direction of these currents, right? And then we'll write the KVL equation of these, two meshes. So let us write the KVL equation here. KVL equation for mesh one is, okay. So let us go. Let's understand this thing. Now here, if you see, okay. So how we are going? How we are going from A to B, B to D, D to then this node, and then back to A, right? This is how we are moving. If we see this current, we are moving clockwise. We are moving, sorry, clockwise, right? So let us remove this one here. Okay, now let us see. Now when this current is moving clockwise, so this current and the direction of EMF both are matching. Because both are matching, so we have taken it as plus E1. Now let us come to the R1 resistance. So in R1 we can see there's two currents are parallel, they are matching. So when they are matching, so I have taken as minus here, negative. Okay, so I have taken as minus here, right? Minus I1 R1. So this is the voltage drop, right? Okay, now let us come to this R2. Now as I come to R2, I see that there is current I1, but this current I2 is also, having some effect in this particular resistance. So the net current here is I1 minus I2. Okay, now since we are as of now dealing with the mesh 1, so we will take it as minus. So minus, because this current is parallel here, and the net current here is I1 minus I2, right? So it is minus I1 minus I2 into R2. So on solving these equations, we get equation number 1. Now similarly, we can apply KVL on mesh 2 also, right? Okay, now let us see the KVL equation of mesh 2. So in mesh 2, we can start with R3. So let us see how they are flowing. Okay, so these two currents are, this is current I2. So these two currents are parallel, they are matching. So I have written minus here. Then let us come to the battery. In battery, we have the battery direction from minus to plus, and these two are opposing, so I'll take it as negative. And then we come to the resistance R2. So the direction of current was this one, so these two are opposing. So but since I am now dealing with mesh 2, so I will take I2 minus I1 and then minus sign here, right? Otherwise, what you can take, you can also write this part as minus I2 R3 minus E2 plus I1 minus I2 into R2 is equal to 0. You can write this also. Why? Because if you compare the directions here, you will have positive sign. Like if you see that this I2 and this direction are anti-parallel, so you'll write positive here, right? But then you will take this current as I1 minus I2. Okay, if you do not want to be fixed or bound with this current, then you can simply take I2 minus I1, but then minus sign will be taken here, this minus sign. Okay, so if you see these two equations, they are same basically. These two equations are same. Then we will simplify these equations, so we get a new equation, which is equation number 2. So in equation number 2, we have this final, this one. So we can say that EMFs are equal to voltage drops. Here also EMFs are equal to voltage drops. Now, okay, now let us take all these two equations all together. So we have this one. This is the representation. So now here in this we know E1, we know E2, we know R1, R2, R1, all these parameters. What are the unknown parameters? I1 and I2 are the unknown parameters. Right? These are the unknown parameters. Okay, so we can solve these algebraic equations to calculate the or determine the unknown currents, means the mesh currents, right? And hence in this way we can find out the mesh currents, and we can apply mesh analysis using KVL. Okay, now there are certain notes mentioned here. Like first is the branch current are the real currents because they actually flow in the branches and can be measured. Now let us come to the circuit diagram here. Now, okay, I'll erase all this first of all, so that this is what I was saying, that because this battery is connected in the branch, so it will force some current to flow in a particular direction. Yes, though that direction can be any, but yes, branches will have some current flowing through them. Branches will have the real current flowing through them. Okay, so the direction of this current could be any, that is not known, that can be assumed also, taken also. But these currents which are in the mesh, they are totally fictitious currents, they're not real current, right? So the mesh currents are fictitious currents and cannot be measured except in those instances where they happen to be identical with the branch currents. Now what does it mean? It means that if so that means we will take the same. If I am assuming that this mesh has I1 current, this mesh has I2 current. So actually this I1 and I2 belongs to this particular branch. I1 belongs to this branch and I2 belongs to this particular branch, because they are independent branches. Now what about this branch? This branch will have some net effect because it is connected to a junction, and here we will apply KCL. That is why by default KCL is also applied here. Though we do not write the KCL equations, but yes, KCL is applied. Okay, thus in branches DAB and BCD, the branch currents are same as that mesh current and hence both can be measured. So this is what I was discussing, that these two currents, they belong to the external independent branches. So here we can write I1 and here we can write I2. Okay, so um, we can, this is nothing but a concept, basically a theoretical concept which is used to solve the electrical networks. So this is all about today's lecture. This was all about KVL and mesh analysis. So in our next video, we will discuss how to solve a network using mesh analysis. So thank you so much, guys.